Okay, so as everybody, probably knows or should know, we have our exam 2 tomorrow, and we can use this time to review any of the topics from Cogbooks or talk about the course. So I'll turn it over to the group.
If no one has a question to start off, I have a question about in T8 for activity optimization 2C. I am a little lost in finding the optimal or the clutch sizes closest to optimum based on the given graph. I was having a really, and then I was going through and like doing that I wasn't understanding it, and I felt like the videos also weren't really giving me a good explanation.
Okay, yeah, this is something we can definitely touch on. This is the one you're talking about right here, right?
Yeah, that's the one.
Okay, so if we read from the question, so assuming that a female invests 1,000 kilojoules of energy in her eggs, which of the following clutch sizes would be closest to optimum? So we're given 1,000 kilojoules, and what we want to find is the tangent line to this curve and where that drops down to the x-axis, because that is the minimum amount of energy we should invest per individual offspring, because after that, the trade-off is it stops becoming efficient. So we want to invest the minimum while still having a decent survivorship. So then we know we have 1,000, and if we draw that line down, we should hit 50. So then 1,000 divided by 50 would give us the 20 offspring.
Okay.
And it is kind of eyeballing it, which is why I think they try to use round numbers, because you got to draw kind of that invisible tangent line and see where it goes down. And as we talked about a little bit on Tuesday, we could test other amounts and see depending on what the answers are. So you could kind of do it going forward or going backward. But the general way is to look at where that tangent line is, find the value on the x-axis, and then just divide by that, because this is per individual and that's our total, and we want to maximize the amount of offspring we can have.
Okay. And then based on like not that same graph, I'm trying to find the exact one, but I can't necessarily find it right now. It's kind of the same thing, drawing the tangent line. I just started understanding how to do it today, but how do you know when you're drawing? So when you're drawing the tangent line, does that also like, do you also draw the tangent line in the graphs for like relative fitness for the phenotypic value? Because according to the answers that we answered to on the activity, like the phenotypic values, like the optimal values or the optimal phenotypes are at the end of some of the lines, like the straight lines, but then for some of them they're at the beginning of the line. Yeah, these ones.
Yeah, so I think it's these answers. So I think it would be, no, these are a little bit different. So those are optimization curves, and these are optimal phenotype curves. So what we're looking at here is we have, hey, everybody, can we put our, I don't know if that's my voice reverberating, but maybe put it on mute unless you're going to participate, just so it's a little jumbled is all. But anyways, back to this. What we're looking at here is a little bit different. So what we have on the x-axis is our phenotypic value, and the numbers are arbitrary, right? They range from 0 to something positive, right? 0 to 50 in this case. I guess not necessarily 0, just 14 to 19. We don't have to worry about what those numbers exactly mean, just where they're located on the x-axis. And then on the y-axis, we have the relative fitness, and an organism is going to want to have a phenotype that maximizes fitness. Those are the types of traits that are likely to be selected for when they're maximizing fitness. And so what we want to do here is just find the value of the phenotype that maximizes fitness. So where are the dots the highest on the y-axis? And then we can see for A, they're on the left side, so we go down, and our value would be a phenotypic value of about 0. And then how would we solve B?
That's a good question.
So what did we look for the first time, right? Where the dots are provide the highest fitness value?
So for B, it would be closer to 19, because that's where the highest fitness value is.
Okay.
Yes, so just even before we look at the actual value, just the right side of the curve is the highest, right? So the
Like
dots
the
are
more
here.
positive.
Yeah, and then we find the
Okay.
highest dots and just go straight down, and that's, you know, somewhere around 19. So I think this is, you know, our best estimate right here. And then what about this kind of curve where we have our stabilizing selection because it's going towards the middle, but where are the dots the highest here?
Around like the 22 mark.
Yeah, so in the middle of the curve, right, which is exactly, yeah, going to be, you know, I would say around the 22 mark. And then how about disruptive selection, where the dots generally the highest?
Around the
Or
50
where's-
mark.
So on the edges, right?
Yeah,
But then it, you know, we could say, why isn't it 0? Why is it 50? But as you said, it's 50 because those dots are slightly higher. So this is on this side right now, we observe the highest fitness.
Okay, so just like, yeah, it's like the more positive, like the most positive values on the graph.
Yeah, I mean, that's one way to think
Okay.
of it as the most positive values, but the most positive on the y-axis,
Yeah.
because that's the, you know, and that's just translated into relative fitness. And that ranges
Yeah.
from 0 of not being any fitness, they won't survive, to 1.0 being the maximum value of fitness. And these phenotypic values, again, you know, they're just kind of arbitrary numbers in this scenario. In real world, they're going to mean something, but we don't have to worry about that in this course, just how to kind of read and relate these charts.
Okay.
Are there any other questions on that, or did that make sense?
That made sense for me. Thank you.
Okay.
Okay, so I was unable to go to Tuesday's meeting and I haven't watched it. I actually don't know where to find the recordings of the office hours.
That's fair. Why don't I'll share my screen real quick and we can actually do that together so everybody has an opportunity to see that. So if you're on the home page of our Canvas for the course, you go into the modules tab, and then we go to module 0, and then it's this listed here as the virtual office hours. And what that'll bring up is I do it by date. So the first week we didn't have anybody attend, so there was no video posted, which is, you know, it's fine. But I just put that so we know why there wasn't a video. And then the other 2 videos from the previous sessions are right there. And
Okay.
I post them. Sorry, what was that?
I just said, okay.
Oh, okay. Yeah, so no worries. Just make sure that we all know where to look for them. That's important.
So then you probably went over on Tuesday the heat flux equations and basically will we have to do the equations or just be able to differentiate which one goes to which?
We did talk about them, but we can treat today as, you know, an independent session. So if anybody has questions, you know, that don't worry about asking if we covered it already, because I know everybody couldn't make it last time. But we did talk about heat flux a little bit. And to answer your question, there will be no calculations using the equations. You will just have to know them conceptually. So knowing what parts of the equation mean what. So like with some of the activities showed, you know, asking in this scenario, what is the most likely part of the equation to change for, say, convection or radiation. So you'll have to be able to do that.
So it'll stay pretty similar to the questions off of the homework.
Yeah, you'll see multiple questions will be very, very similar to the homework questions.
Okay, thank you.
Yep.
Hey, I had a question about something in T8 under the to grow or reproduce chart. There's a chart that shows expected survival path and female age at sexual maturity, but I was a little confused on how I was reading it.
Sure. So we're talking about this chart, right?
Yep.
Yeah. So on the y-axis, it looks like we have expected survival past sexual maturity. And that just ranges from 0 to 6, and that's time. So it's in years. So this is assuming that they've already reached sexual maturity and how long they live after that. And then the x-axis is female age at sexual maturity in years. So what we can do is look at different points on the graph. So if we look at, say, the fish and the shrimp, so their age at sexual maturity is ahead of expected survival past sexual maturity. So it looks like they reach sexual maturity at a younger age and don't survive as much beyond that. So really the steepness of the curve will say they'll survive better after they reach sexual maturity. So they'll reach later stages in adulthood, and the less steep curves will mean they don't, it means the opposite, right? They'll reach sexual maturity quicker and won't survive very long afterwards.
Yeah, it was very early in the morning when I was looking at this. So I get it now. Yeah, so like the fish, say we're looking at the fish and shrimp line all the way at the end at 7.
Mhm.
They reach sexual maturity, but it's also the end of their lifespan, or that it's like there's 3, right? And that's this. So basically, that fish reaches sexual maturity at the same time that it dies. Is that how I should read that?
Or, well, it depends on where on the line. Like, so say we read it all the way at the end. If it takes 7 years to reach sexual maturity, it'll only live for 3 years beyond that.
Oh, okay.
If it reaches sexual maturity at age 3, it'll only live, 1 year beyond that.
Okay. Okay.
And the
Okay,
bird
thank
is a little
you.
bit opposite, right? If it reaches sexual maturity at 2, it'll live quite a long time past its sexual maturity. It'll live to 4 more years.
Okay. Now I'm grasping it. I think I was just reading it backwards.
No worries. Yeah, I mean, it's at first glance, it took me a little bit to kind of understand what it was, because it has, years on both of the axes. So it's a little confusing at first.
Yeah, I think that's what threw me off. Thank you.
Any other questions about this plot from anyone else?
I did notice on some of these under T8, there wasn't like a huge amount of information. I came across the same thing that I came across that we talked about on Tuesday, where when you go into the extra information, it provided all new stuff. So I stopped looking at those.
Yeah, I mean, I recommend still going into them, but if it does provide brand new information,
Yeah,
then maybe those aren't ones that will stay in this course to the next session. And I'll have to go through those with the developer, maybe clean that up a little bit.
yeah, there were like lots of new definitions and stuff. I was like, okay, I don't feel like I need to.
Yeah, and that goes for everybody, obviously. If there's new definitions, like bold terms, like if they talk about stuff, like you see this in the main text, if that's in the supplemental materials, don't worry about it. It's not going to be on the exams. I'm not sure why those were put in there, to be honest, and I think we can maybe get that cleaned up.
I think those are there because they reuse the same material in multiple different courses. Because I've definitely had pages show up that I've done in a different class.
From this course has been in a different one?
Yeah,
Huh.
it's happened in multiple different classes. So like the substitute, like to help you understand the page that you're currently on, might have been from a different class as well. So that's why everything's still highlighted and stuff, I think.
I was gonna say the same thing. I noticed that there was like 1 or 2 old biology courses that I took that I'm seeing not the exact same information, but it's like very similar.
Was that from like 181 or 182 possibly?
Yeah, 182.
Because I think the course creator of this taught BIO320. He created this course, but he also taught and I think created some content for 181 and 182. So that could be why.
Yeah.
Yeah, I did notice that. Oh, go ahead.
No, go ahead. Mine is separate.
Oh, I just noticed that there was lots of references to material that we didn't go over. So
Yeah, I was gonna say, I think it was in T8. I don't know if anyone else had this happen, but that video that the professor had posted, for some reason it came up on mine twice. But like, so the first time that it did, okay, the first time it was like one big 18-minute video, and then the next time I saw it, it was like the case, so it was split into 4 different videos. I was like, why?
The same on
No.
mine.
Okay,
Yeah, that happened to me too.
that was weird.
It should happen equally for everybody. Hope so. The content's the same. I hope at least. I mean, it's not great that it repeated itself, but I appreciate you letting me know.
So I have a question also in T8. What about like energy invested in survivorship? I think it's what I'm looking at is activity optimization A. And I get a little confused with, I think it's when we're thinking about like energy invested in like optimization, are we supposed to like really think about how much energy is put in for the mom, like whoever's like producing the offspring? Is that how we like should kind of look at it, as opposed to thinking about like the survivorship of the offspring? Or is it a little bit of both?
It's generally geared at the mother because that's the one that has to spend the energy to create the offspring. Some of it can be like how much individual energy is given to each individual offspring. So like the previous one, we went over the optimal clutch size.
Mm-hmm.
So like we can, I mean, there is a little bit of information about how much is given to the offspring, but that's not really going to be related to survivorship. It's more this energy per offspring. So I'm trying to think how to word it. Yeah, because this energy invested per offspring is from the mother. And then this survivorship is the survivorship of the offspring, because there has to be a minimum amount invested to give them at least 50% or higher. But we don't want to do too much because then the rate of return declines. So that's why we talk about the tangent line.
Mm-hmm.
So I guess the answer is it's both, right? Because this on the x-axis is concerned with the mother, and then the y-axis is concerned with the offspring. But because she's the one creating the offspring, that's why they're both on the chart.
Okay, so for question 3, I think the answer was, yeah, so product of the number of offspring and survivorship, is that like, so that's the mom and the offsprings also survive?
So no, this is the survivorship of each offspring.
Okay,
Yeah, so this is concerning both of the offspring.
okay.
This question confused me a little bit. What would be the difference between the product of the number of offspring and the sum of the number of offspring? I guess I couldn't tell which one would be more correct, and I couldn't.
Well, it's the way that it's the way that the math is set up, because you have like something times x equals y, and then you have to multiply the two together to get y, versus you don't add them together.
Okay.
Mhm.
So that goes, it's like trying to think if I have an example in my notes real quick. Yeah, so it's this equation where if you it depends on what question you're asking, you can reorganize it, right? Where you would have two numbers right here, it's division, but if you switch it over, you would have multiplication on the other side. So that's the whole point of the product, just being multiplication, and versus the sum would just be addition, which is not how the equation goes.
Okay.
And will the equations be provided on this exam?
Since there's no
class.
math on the equation, and there's no math on the exam using the equations, it's focused on the conceptual side, the equations will not be provided.
Okay.
So for this test, can we have scratch paper, or is it even really needed? Or just,
You can have scratch paper, that I'm fine with that. You can have scratch paper for every exam. Some people like to write on their scratch paper first from memory so that they can have some stuff to recall. So that's one way people use scratch paper when there's no calculations.
So can we go back to equations in T5 for a second? So like conduction has, you have to understand body surface temperature, the ground. So we need to have that, what each of those means memorized.
Yes,
Okay.
because like some of the activities might ask you what, if we have these equations, it might ask you what part of the equation is changed the most between two pictures. And then that way you would say, and those would be multiple choice questions most often, or potentially true, false. So you'll see the parts, the letters of the equation. If you see A, you have to recall that that's surface area. If you see, T, that would be the temperature, or in the other equations, what L is the distance of the energy has to transfer. So it's, you don't see the full equations, but you will see the parts when like the individual, you just have to know what they are and the
Okay.
conceptual part of them.
My brain works better that way, so I understand that. Thank you.
Okay, no problem.
Can we talk, so under, I'm going back to T8 because that's one I've most recently been in.
Sure.
So under life history traits, one of the things that was mentioned is that generally each individual only replaces itself regardless of how many offspring it creates. And I know that there's a variable included there. Otherwise, populations would continue to expand like basically humans have. But I know that they vary across. Are we gonna have to understand what those variations are outside of what their life form, habitat, environmental conditions? Because what it said in that section was that the variation of one trait often correlates to other traits, and most variations can be organized along continuous values. Are we going to need to know how to organize those? There wasn't a lot of information provided there. So
I'm not sure I'm fully understanding the question. What
No.
exact section is this from?
Let me go into it.
Sure, and that way I can see what they're showing and what would be expected.
I think this was.
Kind of like they give really specific examples of the trade-offs, and you want to know if you need to know each one.
Yeah, that's what I was looking for. But I don't remember where I pulled this from. Probably the first section.
So,
History stems from organism uses.
okay,
Like the one with the female sockeye salmon. At the bottom, it says 2 points can be made about this variation in life's history. Oops, sorry, my dog is underneath me. Now I don't see where I pulled those notes from. Oh, it's at the top of the slow to fast life history continuum.
so for this part, it talks about like the slow to fast, yeah, you said the life history continuum. So knowing what the difference between slow and fast are.
Okay.
And what some of those trade-offs are. Like, later it gets in a little bit more detail, like where it talks about the cost of reproduction to grow or reproduce. So in some instances, why, a question could be is why would it be beneficial to have age at, sexual reproduction later in life for some species, whereas it might be better to have it early in life for other species.
Okay.
Can we think of, if we want to try and answer that to sort of the discussion, what would be beneficial to having age of sexual reproduction late in life?
Greater size. So, if you're larger size, typically that means like for the female, they can produce a larger sized offspring, which given variable conditions of the environment might have a better chance of survival.
Yeah, or maybe they could also produce more offspring, right? And that's another trade-off is have few large or many small. Would it be beneficial for a short-lived organism to reproduce late in its life stage?
No.
Right, so that might be the opposite answer, right? Why would it be beneficial to reproduce at a young age? Because if you're not a long-lived species, say even like Drosophila, they only live like maybe 30 days. So if they start reproducing on day 28, the probability of surviving to day 28 is low. So that therefore their fitness value goes down, because if they're waiting that long, if they reproduce in the first 5 or 6 days, the probability of survival is high. So they can reproduce maybe multiple times in their lifetime, or at least once before they die.
And
So
would
the-
it be, if you had a shorter lifespan, would it be more fitness if you produced more offspring versus less in that scenario? Or would there more variables would need to be account for that?
I think you can make an argument for more offspring, right? And part of that trade-off then would lead into the argument of what is the probability of survival of your offspring. If it's low, then you want to produce many. If it's high, you might want to produce fewer, but put more energy into them. So I think, and that's where it gets into this, the species specific and the fast or slow life history trait, like where are they on that continuum?
So as long as we're understanding, like, a longer lifespan generally is also related to low offspring and high parental investment sort of thing.
Yeah, parental investment is another trade-off, right? If you have, 100 or 1,000 offspring, parental investment goes down with the number of offspring you tend to have. Versus if you have fewer, you can invest more time and energy into those individuals. So yeah, thinking of everything as, a trade-off. If you follow one life history trait, what's a positive and a negative? I would think of, if you follow a different one, what's the trade-off, the positive and the negative? And sometimes they do tend to go together, like on the fast life history trait, they tend to be smaller, short-lived animals that have developed their offspring early and have many smaller offspring. So knowing which kind of traits are linked between fast and slow would be a good thing to understand too.
Yeah. For an example, species that have more risk of predators would probably want to produce earlier and more.
Yep, that's a good example too. Predation plays a role. And similar competition could play a role where the males might wait till later in their life to reproduce if it's a highly competitive species, because a larger body size gives them a competitive advantage. So they might have higher success of actually reproducing and finding a mate if they're bigger. So it could actually affect females and males within a species differently too, depending on their ecology and how they interact with their mates and their competitors.
Kind of on the same topic of the life history. I'm looking at the study guide, like
Sure.
the study guide for question 11. Describe the phenotypes that constitute an organism's life history. Is this meaning like the actual physical characteristics, or is this more because like I don't have my notebook out right now, but I remember reading, I'm gonna pull up. I remember reading about I hope I'm saying this right, the fecundity.
Mhm.
The fecundity, the parity, the parental investment, and the longevity, would those be considered phenotypes, or are those like different factors?
When it talks about the life history 411, those are the physical traits that we've kind of just been discussing. So what I have a list of them in my notes, one being size at sexual maturity, age at sexual maturity, number of reproductive events in their lifetime. Do they mate, multiple times and have multiple clutches, or do they have like a single or one or two offspring events?
Okay.
Their longevity, lifespan, as we mentioned, number of offspring produced, we mentioned, the size of the offspring, and then as you just mentioned, level of parental care.
Okay, because I wasn't sure if like the phenotype was looking for the actual like physical trait that one would see, or if it was the one that the organism like plays out in its lifetime. So it would be all the ones that you just mentioned.
Yeah, and it's kind of both, right? A phenotype is what you visually see. So if it's larger size, the phenotype could shift to being larger offspring.
Okay.
It could also be a behavioral trait that you observe, saying the level of parental care too.
Okay, so it's pretty much just any like biotic factor that would contribute to reproduction of that organism.
Yeah, I think that's a good way, fair
Okay.
way to put it.
Okay.
Yes, I think the only other thing I had in my line is, I think they define life history as the schedule of an organism's growth, development, reproduction, and survival, which is essentially what you were saying, so.
And just as a quick question, I think one of the other students may have mentioned that there was a study guide available.
Yes,
Is that accessible on like the modules? I couldn't seem to find it.
yeah, no problem. We can, let me share my screen and we can do a visual of making sure everybody knows where that is too. That's also important.
Okay, cool. Thank you.
Yeah, so just on the homepage of the course again, you go into the modules. And then for each individual module now, so we're already done with module 0. So what we'll do now is we'll go down to module 2. And it's always at the beginning. It'll be module 2, topics and learning objectives. So it doesn't call it a study guide. But if you click on that, it has some questions that, you know, are good for review. And some of the exam questions have been built off of these too.
Tyler, you in the Discord for the course?
No, I'm not.
If you want access to it, it's been really helpful for me at least, because like we'll post questions in there like based on other students' understanding.
Mhm.
And I've gotten a lot of really good resources from there. So if you want, I can send you the link to it.
Yeah, that'd be awesome.
Would you mind, or somebody, there was another student that I talked to earlier today that I don't know how to access the Discord, and I'm not really looking to be transparent, but they were asking about it. And I don't know, the easiest way would maybe if somebody could post it on the course community forum discussion, a link to it. Or however you guys are sharing it, but I know other students have asked for that too, so. And I think it's a great idea, you know, it's a great way for the course, you know, because it's online, it's hard to interact. That gives you guys more resources for each other that you guys can study together and help each other answer questions too.
Yeah, I just copied it. So I'll just go in there right now.
Awesome.
Yeah, I'll just copy the link right now.
Can we go over also in, I think, P8, critical thinking, optimal egg size, this graph with the, I think it's lizard eggs with the male and female ones. I think again, it was like the one I struggled with was number 3, where it was kind of like, I think also just having to take consideration the like what's best for the mom. If a lizard could control the sex of her offspring, which sex would she produce? Sorry, I got cut off. Which sex could she produce more offspring of the optimal size in the spring? So I think for this, it's like I get a little confused because there's more like looking at the chart, like the female is higher, but then like smaller eggs would be better for the mom, or she could produce more of them at like lower energy expense. Is that like the logic to this?
Yeah, so I think it's, so we can all see it. So we're talking about this chart, right?
Yes.
Okay. And then we have survival to maturity, and then egg mass. And it talks about larger eggs enable female offspring to survive better in either spring or summer, but had only weak positive or negative effect on the survival of male offspring across seasons. Yeah. So looking at it, it seems that, you know, survival to maturity for the female offspring in either season would be better to have larger eggs up to a point where this starts to plateau. So maybe up to 0.6. But for male eggs, when the egg masses got larger, there was really no benefit to it. So having smaller males, again, in either season, you could argue maybe a little bit bigger eggs would be better for males in the spring compared to or actually it would be the opposite. It would be for in the summer compared to the spring because they do cross. And the third question was, okay, so it's saying because we don't see where it actually hits the y-axis, but if we would just continue to draw it straight, we can make a like a guess kind of which one would be better.
Mm-hmm.
So does that make sense on more how to read the chart, or?
Yeah, I think so. I think it's like the visual and like what the chart is actually saying, like just
Mm,
get flipped in my brain.
yeah, so
Where I want to say like more like bigger is better.
and in
But
some
like for the
instances that's,
males, I'm like looking at the left side of the chart instead of the right side of the chart. I just get like flipped around.
I mean, it depends on where we are, right? Because both of them technically cross. So in the summer, yeah, I said bigger males would be better, but in the spring, it really doesn't, it actually smaller males would be better.
And then to answer the question of like, so if she could control the sex of her offspring, she could produce more offspring of the optimal size in the spring, do we choose like males because, like, why do we choose males over females, I guess?
If we're thinking in terms of energy from the mother, these egg
Mhm.
masses are smaller, so it's going to require less energy for her to produce the same number of eggs.
Okay.
So she might have like a male rich clutch. I mean, eventually they do have to produce females or the species would go extinct.
Right. Okay, that helps. Thank you.
Good. No problem.
It might also help. I had trouble because there's just too many lines crossing in this one. So I took spring and kind of like separated it out and then did summer on a separate little like graph of my own. And that helped me understand it a lot more.
Yes, that is such a good idea.
Yeah, it would definitely simplify things. You could focus on the question, what information it's asking, rather than having to look at all of it at the same time, which can be a little challenging.
Would you mind going through the Grimes diagram? Talking about stress tolerators, competitors, and reader roles.
Sure. Is that in? Which section is that in again? I just
That's
saw
in
it.
T8. I think
It is in
that's
T8. Okay.
Under,
So I think it's the life history traits of
Yeah.
plants, right?
that's the one.
All right, let me. Okay. So that's this diagram, right? So what this is showing is it has 3 examples of the different types of plants. So the rudderals, the stress tolerators, and the competitors. And it's not telling us a whole lot, to be honest. What it says, like, increase in competition. It's the highest in goldenrod as the example, because they're a plant species that's very competitive. And I think it's just really showing the different types. I mean, I'm not seeing a lot of information coming from this, other than possibly where they overlap a little bit. I think that this box down here is much more important because this tells us the traits that go along with those types of plants. So it tells us what stress tolerators do in these four, right? We have potential growth rate, age of sexual maturity, proportion of energy used to make seeds, and importance of vegetation reproduction or vegetative reproduction. And just knowing that, what one of these plants would have, which one of these would have a potentially slow growth rate might be a question. And that would be, right, the stress tolerators compared to the competitors or rudderals. And we might think about why. Why would the growth rate of a stress tolerator maybe be slow?
It doesn't have as many resources to grow quickly with.
Yeah, and if it might be waiting on a certain season, right? So say in the desert, it's dry and arid for most of the year, but they have a rainy season. So it might be slow growth, so it doesn't burn out its resources for reproduction until that rainy event. And then all of a sudden it grows, it flowers, and sends off its seeds in that short time period. And then that, we could argue, then it has a late age of sexual maturity because maybe the monsoon doesn't come through that year. So it has to be a longer lived plant and wait on that monsoon to come, and could take a couple of years potentially. And then if we talk about the proportion of, energy used to make seeds, it would be low because they can't keep those seeds alive for a very long time. And they maybe want to produce lots of them since they have a low probability of surviving in a stressed environment. Why would the growth rate be the opposite in like plants that are more competitors?
Better access to resources, and like literally like just kind of pushing their way in wherever they can. So there's probably a lot to take from.
I mean, if they're highly competitive, they might have limited resources, right? What's a limited resource for a crowded area of plants?
Light.
Water, light.
Yeah,
Soil.
water possibly. Light is the one I was kind of thinking of. So if you grow fast, you're above those plants, so you can kind of overshadow them and make sure that you get your sun. So you want to grow really quickly and reproduce as quickly as you can because you have a low probability of survival.
Would soil be a factor as well?
It could be, but I think this is considering the plants their seeds have already landed. So this would be like growing together with other plants. I mean, because you can't, as a plant, you can't really move like laterally. So if you're in a bad place of soil, you're kind of stuck with it. But it could be that if you reproduce at a young age, your seeds have a higher probability of reaching that fertile soil and growing sooner and outcompeting those competitors.
One thing that helped me with this is that invasive plants often grow faster than the native plants surrounding them. So they're usually competing for light resources. And that's why invasive plants often outcompete the natives, which are generally slower growing.
Yeah, they tend to choke them out essentially, or shade them out to some extent too.
And then at an energy point, so we see the energy used to make seeds is low. Is that because they use most of their energy to increase their growth rate?
Exactly, that would be a trade-off, right?
Okay.
They might have a lot of resource available, but they're putting so much into growing fast that it's that allocation of resources. If you put energy into one trait, it pulls maybe from another trait.
Can we touch real quick on just one thing that I was a little confused about? Well, not necessarily confused, just looking for clarification. we're under the principle of allocation. One of the things it talked about was larger females often produce more offspring. Does that mean larger females just within that species? Because obviously like an elephant versus a fish is very different.
Yes, I think that would be species specific. And that also goes into, there's, connected, another trait would be parental care. Fish don't have high levels of parental care, so they might produce more offspring versus elephants have high levels of parental care and therefore generally produce fewer offspring. Did that have an example? Like which tab was this in again?
It was under the, it didn't have an example, which is why I just
Oh,
sort
okay.
of, it, I mean, I have a tendency to read too far into these things, so.
No, but that's why we have these, have a discussion about that. It was a good question.
I have a kind of random question. If we go to T5 activities, process of heat flux C, in that one, it put the cat as being conduction and the lizard as being radiation. And I can see them being both, but I would have thought that the cat would have been more so radiation and in the lizard more so conduction, because the lizard is trying to keep its feet off the ground.
Sure. And
The
I will
cat's
say,
breathing in the sun.
sorry, what was that, the last part?
Oh, I was just saying the cat's like literally soaking up sunlight. So I mean, I can see both sides, but if I just was to see that on the exam, like how would I know which one I was supposed to be looking for?
That's a good question. And I'll say you can make the argument that all three of these are in all three of the pictures, right? To some extent. So I think the best way to think about these is what is the best answer, not what is the absolute correct answer. So, because if we look at the cat picture, we could make, is there evidence of convection, which would be, the passing of a gas or a liquid? It doesn't appear to be very windy, but, there's probably some level of heat change through convection there. If we talk about radiation, we can see that it's light out, so the cat is certainly absorbing solar radiation. And then conduction is physical contact with an environment. We can see that there's a large portion of the cat in contact with that environment. So based off of those three arguments, what would we, maybe tend to lean towards is the highest rate of heat flux in this picture?
So what's the logic like for conduction being the best for the cat there? It might just be on I behaviorally knowing what they're doing is getting in the way of me being able to understand that part, but these two
Sure.
were.
In the way the activity is set up, it's a process of elimination. So for that one, maybe we don't have a good answer yet, right? I would agree. Like we could say it's probably not convection, or at least that's the weakest one, but there's good evidence for radiation because I agree it's out sunning itself, but the sun's out, so it's probably warming this block. So it's probably gaining heat from conduction as well, because that's the physical contact. But now if we look over at the lizard and we go through the same processing of all of the events, again, there's no blowing sand. So there's, little evidence of convection, I would say. Radiation, it's light out, so it's certainly, there's solar radiation happening in this picture. And conduction now, part of that equation is surface area. How much surface area of the organism is in contact with that in another object? And we can see that the lizard is, its stomach, its head, its tail, 2 of its feet are off the ground, and only 2 of its feet are actually on the ground. So there is definitely conduction happening, but it seems that it's minimal in this picture. Would be my argument.
I get it now because I just reread the actual like prompt, and it's we're right here, we're looking at the heat gain. So that makes sense now. And I guess I was just overthinking it.
No, but I mean, I think this is a really good point, because again, we said in the beginning, all 3 of these heat fluxes are happening in all 3 of the environments. So there's no wrong answer. It's just which is the, the strongest processes. And then convection is almost, if there's a picture of something in water, 99% of the time, because the heat capacity of water is much higher than that of air, it's almost like you're almost guaranteed that it's always going to be convection. And then through process of elimination, then we could argue this is radiation, right? And just to double check it, I think I put them on there backwards. At least that's what I meant to do.
Yeah, I was just
yeah.
getting stuck on the behavioral aspect of it, knowing that the lizard's trying to keep his feet off the ground.
Yeah. And I wish they would honestly provide a little bit of context, tell us what the environmental temperature is, like a lizard in a hot desert environment, and tell us the lizard's body temperature and the sand temperature. That would make it a little more straightforward. Knowing that the lizard's cooler than the sand, obviously it's going to be gaining heat from that source then. Yeah, and somebody mentioned in the chat saying about the cat, there's more physical cat on the ground or its surface area on the ground, which leads to more conduction. So awesome. Anybody else have any specific questions or anything they want to go over?
Nope, I'm good. Thanks though.
Okay, yep, no problem. And I'll be available via email tomorrow too, in case anybody thinks of any last minute questions before the exam, because you can take it at any point in the 3-hour period tomorrow. So
Okay, thanks again, Travis.
yep, no problem. All right. If no one else has any questions, I think we can call it a session. I appreciate everybody coming on and asking questions and facilitating this discussion. I'm sure your classmates that weren't able to attend will appreciate it as well, so they can view the video.
Thank you for your time.
No problem. Have a good night, everybody.